Welcome everybody to DAT447, using graphs over your data lake to power generative AI applications. Quick shout out to the tech team here who worked through a couple of last minute presentation issues. I'm Brad Beebe. I'm a director with AWS for Amazon Neptune, and I'll also be joined today by my colleague, Dr. Umit Kalyurik, who's an Amazon scholar and is also with the Neptune team. Before we get started, could I see a show of hands of folks who are using graph processing on your data lake, either graph algorithms or graph query pieces? Okay, a few. How about people who are using different techniques, including graphs, to improve the accuracy of generative AI applications? Okay, cool. Well, it should be a good talk. Graphs are awesome. And the reason that they're awesome is because they allow you to use the relationships in your data to be able to solve problems and ask questions. In a graph data model, relationships themselves are first-class entities. You can query them, you can traverse them, you can write algorithms and programs that iterate and loop over them. And this enables all kinds of super interesting and valuable graph applications, from finance and fraud detection to knowledge graphs and engineering models to customer 360 and profile pieces. One of the things that I've seen, and I joined AWS almost 10 years ago to start what's now the Neptune service, is that the most successful businesses and companies and applications, they find a way to use a graph to do something remarkable for their customers, to provide some sort of unique and interesting function. A great recent example of this is Wiz. Wiz is a large cloud security posture management company. They started with a vision of the world as a graph and context is king, and they used that to reimagine cloud security posture management. And we had the benefit of being able to watch them along the way over a few years. And one of the things that struck me about what Wiz has done that many other people have tried in different ways is the way that they used graphs not just to connect data, but also to help explain findings and give you a way that you can ask questions and understand quickly, why is this the most important thing? Or why is this the right answer? We often quote that there are many, many problems in the world that can be solved by graphs. But as practitioners, as people who are building applications, we need to keep in mind that graphs themselves are not an intrinsic benefit. You're not actually, if your end state is, and now I have a graph, you haven't really accomplished anything in your application. And over the last year, 18 months, we've seen a huge increase in the number of customers who want to improve the accuracy of generative AI applications, who want to use data on their data lakes and try and get more insights. And so today, what we're going to go through is a couple of different strategies about how you can do that. How you can do useful things with your graphs where your data lives. And so I'm going to introduce Umit to take you to the next part.
Good afternoon, everyone. So I'm going to walk through two of the strategies we have been using, and you can use in your applications as well. So the first one, we're going to look at taking your data from your data lake and using it in a graph. These cases, you know that there is a graph. Either you created the graph or you want to create the graph, and we will see how we can do this today. So Neptune Analytics built on top of a unified graph data model. So it's called One Graph Model, and it's a logical model that unifies both property graphs and RDF. so that you can actually load both RDF data and the property graph into Neptune Analytics. So you could import your data, start your graph with that way. But after you start the graph, you can also use tabular data that sits in your data lake using your favorite graph processing language, OpenCipher. So you can query the data sitting in your data lake with OpenCipher, and you can import and export to your data lake as well. What are the use cases to do those? Let's say that I have an airline data set. I have the metadata information about airports and their connections, but I don't have most recent airline flight information. Let's say that that sits on my data lake. We can actually read that and process that. We can read that and federate with our data sets. Let's look at how we do those. The first one is reading from your data lake. So we developed Neptune read algorithm. What it does, if you have a data set, either a Parquet format or CSV format, you can load your data set. All you have to do is tell the format, this is the format, Parquet format, and it sits in this S3 URI. Then what it does, it returns every single row of that data to you, and you have the direct access to columns, and you can use those columns. You can do the same thing with CSV files as well. Okay? So let's look at an example how to use this. Let's say that the scenario I've just described, we have the S3 data table, S3 file. It's a Parquet file, and it consists of multiple columns like carrier, flight number, origin, and destination. And you want to read that. You simply tell this is the URI, this is the Parquet file, and it returns this row by row. It's an OpenCipher. You can use those columns as you wish. You can take carrier information as it is. You can concatenate origin and destination with an arrow between, and you can produce the output like this. This is just reading your graph. You're reading data in your graph language. Okay? Of course, we can do more. We can federate the data. Let's say that you already have the airport metadata information about the airports. And what you want to do, you want to get the most up-to-date recent flight numbers by each carrier. Okay? You can start your OpenCipher query with a match clause, asking for airport 1 and airport 2, and specifying their code to be JFK and Las Vegas. So you're trying to find all of the flights between those two locations. And you call Neptune read, giving the same Parquet file. So it's returning each of them row by row. So what we want to do, we want to filter that so that the airport 1 and the origin and airport 2 and destination match. If they match, you want to collect the carrier information and all of the flight numbers, but you want to combine all of those flight numbers as a set, basically. And you can use collect intrinsic for that, and you can return the results. And you'll get an output something like this. Okay? So we federated what we have in our graph and what we are reading from data lake. Right? So we can also augment our graph with the data. Let's say that we want to create an edge between airports. We want to create a new edge. We already have the route edge between them. We want to create a new edge flight for every carrier that's flying between those two airports. Okay? So for example, in the first row shows that between JFK and Las Vegas, B6 carrier is flying. So what we can do, we will have a very similar cipher query. We'll again specify the first node and the second node as JFK and Las Vegas. We will have the same filtering. This time what we want, we just want the distinct carrier information because the same carrier may have multiple flights. We just want one of them. We ask with the distinct, and we can actually create a new edge with this information and augment our existing data. All right? So that was strategy one. When you have just data and you either have a graph or you don't have a graph, you either get the data and process like a graph or augment, etc. So these are simple cipher queries. What if I want to do something more? What if I want to do some graph algorithms on that? Okay? So what's the graph algorithms are useful for? There are many graph algorithms, and they serve many different purposes. In one scenario, let's say that I have a graph that contains technical research information, okay? And I want to understand the importance of a research or researcher, okay? So I may have a graph of airports. I may want to understand the importance of airport in terms of the closeness of that airport to the other airports. Or I may have a customer graph. I may want to investigate the most influential campaigns I can run, okay? Or I may have financial transactional data, and I might be interested in identifying frauds. In these cases, we use graph algorithms. Graph algorithms will run on whole graph, not just giving a single edge and two pairs. And let's look at one graph algorithm, okay? So one of the most commonly known algorithm is Google's famous PageRank algorithm. Many of you might already be familiar. My apologies for the repetition, but how do we define the importance of a vertex? So to find out that, we need to look at what are other vertices pointing to that vertex, right? Who is following you, right? So that's the first step. The next step is for those, of course, we need to repeat the exact same step. We need to figure out who are following those people. As you can imagine, this goes recursively for the whole graph, right? So the PageRank algorithm is basically operates like this. For every single vertex, the importance of a vertex is the average of the importance of the vertex connected to that vertex. So that's one way of describing, and that's the formula that I'm showing here. So the second term is basically getting all the importance of the vertices that are pointing towards me. The first term is some randomization so that you can do random jump and smooth basically the process. Of course, this algorithm can be implemented many other ways. So this is the one that looking from the destination perspective. You can think of this looking from the source. You may distributing your importance to your neighbors. Or another way of looking at, for every single edge, you take a ratio of the source's importance and this giving that to the destination. So there are different ways to implement these algorithms, and how your data is laid out will define which one of them is performing well, okay? So, but you don't need to worry about all of these things, how these are implemented, because we implement these algorithms as efficient as possible in our data structures, okay? All you need to know is how to run these algorithms, okay? So this is the cipher call to run PageRank. We have two versions of the PageRank, this one called mutate, what it's doing, it's calling a PageRank on the existing graph. It's asking the result of the PageRank should be written to the property called score. It's basically a PageRank score. Okay? So PageRank algorithm, I guess I skipped a little bit too fast, is not a one-pass algorithm. You need to go over the graph multiple times. You need to do that iteration multiple times, and either user decides how many times they want to do. Maybe you run this algorithm multiple times in your graph, and you know that some numbers is sufficient. Generally, PageRank algorithm, 10, 20 iterations more than sufficient. Okay? And you tell which vertices you want to run this and which edge labels you want to use, and you run the algorithm. Of course, after you run the algorithm, you have the score in your graph. If you want to integrate this score with other processing systems you have, you want to transfer this to your data lake, you can do this by using an export command. You can basically specify, hey, for every airport edges, I want you to write the score I computed, and this will give you a table in basically a table format with each of the PageRank scores. Okay? So that's one of the algorithm. So another algorithm commonly used are centrality algorithms. Centrality algorithms are useful to identify the important vertices. In this toy graph, you may identify the source of the problem, the culprit, the Arthur, the guy hiding himself, sits in the middle of all of the connections. So obviously, Arthur is very vital for passing the information between those two sides, and also sits in the middle of the graph and close to everyone, right? So there are different centrality metrics. Closeness centrality is one of them. And closeness centrality, what measures? It measures how far each of the vertices from you, okay? And it normalizes. The challenge, obviously, to run this algorithm in the whole graph fast. So let me give you the just simple formulation, an algorithm to explain how this algorithm in general works. So given a graph, what you do for every single vertex, you go over the distance to all other vertices and you sum them up. So you compute how far this vertex from everyone else. And closeness centrality is the reciprocal of all the vertices, all other vertices, and -1 divided by how far you are. This is one of the formulation of the centrality, which is basically normalizes, so the number is between 0 and 1, and easy to interpret. Okay? If you run the closeness centrality on this toy graph, you will see that Arthur's closeness centrality is very high. So you can identify that. How do we do this? So the algorithm starts with, for every single vertex, you need to compute its closeness centrality. For every single vertex, what you need to do is you need to run either a shortest path if the algorithm, if your graph is weighted, or simple BFS if you're running on an unweighted graph, and then you write the output by normalizing. Okay? So I just want to highlight this BFS is obviously your standard BFS algorithm or single source shortest path. The best you can do is you need to go over all of the edges at some point in time. Then an outer loop over all the vertices is going to take quite a bit of time. So this is a very expensive algorithm. So obviously no one is running such algorithm in large scale. What you do, you usually sample a random set of vertices. Okay? And in Neptune Analytics, we do much more than this. We do other HPC optimizations like vectorization, and parallelization, obviously, to make this algorithm run much, much faster. But again, for you, what's important is how to use this algorithm, right? So all you have to do is tell, hey, I want to run this algorithm on airports. And when you call, you can either specify how many source vertices you want to give. If you give a maximum number, you're going to run an all graph. And you specify which routes you want to run. Then it will return the score. And we will here printing just the description of the airport, which will give you a human-readable form and showing that Charles de Gaulle is the airport that has the closest centrality. Okay, so we have a suite of algorithms implemented in Neptune Analytics that you can use. I just showed you just two of them. We have different class of the algorithms, like pathfinding algorithms, simple breadth first search, looking the connectivity between a single vertex and how others are reachable. Shortest path, again, starting from a single vertex, using the weights and how far other vertices are. Or if you're interested with just going 2-3 hops and just getting a limited set, you can either use top K hop limited BFS or Ego network if you're only interested in one vertex and its neighborhood. Centrality algorithms, I already mentioned two of them, and degree is obviously the third one, just computing the degree of the vertex. Then clustering, if you want to find related vertices. This will be a great algorithm for fraud detection. So you can run any of those algorithms depending on your graph. So starting from the simplest one, which looks at weakly connected components, how the vertices are connected, going to the label propagation and Louvain. And we have a set of algorithms to look at the similarity of the vertices. And most interestingly, which Brad will talk about more, we have about vector algorithms that you can use to search the vertices that are similar and use those vector distances. So the vectors come from LLM, GNN, many other sources. Whatever you have the vectors, we can use the vectors as the vertex properties. So maybe if you want to play it yourself, if you want to see how you can use the algorithms, this will be one use case you can try yourself. If you use the QR code, you will get to one of the notebooks that we set up with the example case. So in this case, the case study is about using PaySim, which is mobile payment transactions, and we are trying to find the fraud. So the data is in S3 tables in this case. Okay, what you can do following the notebook, you can load the data from S3 tables to a graph. Then you can run Louvain algorithm on that graph to identify the communities. And you can obviously export it back, those communities, to be used by other upstream processing you may have. Or you can even use the visualization enabled with the Graph Explorer. Okay? So I described the cases where you know that there is a graph and you want to run some algorithms. So now Brett will take over you to vectors, and when you don't even need to know that there is a graph.
So now that we know about graph algorithms, let's look at a different strategy where we combine vector search and different kinds of graph traversals. So if you think about searching in vector space, when you find things that are similar, you're taking a distance measure from basically a high-dimensional matrix. And it's a super powerful technique. It lets you find images that are similar. It lets you understand that a zucchini and a courgette are most likely the same thing. But if you're trying to build an accurate application, you're trying to explain the results to someone, vector similarity search is really kind of a black box. You can't tell why some things are related. Contrast that with a graph traversal or a graph search, and if you ask something like, why are Wang Shulan and John Doe related, you can answer it with a very explicit traversal and say, they're related because they acted together in these movies. And it may not be as flexible necessarily as vector search, but it's certainly very easy for you to explain. And so one of the things that we've seen customers do is look at combining these different types of search. And so this is one example of hybrid search, where a user asks a question, and you use a combination of different techniques, maybe a conventional inverted text index, a vector similarity search, a knowledge graph. And you combine those results to be able to give the user a better answer. Building on what Umit showed you, it's very straightforward to create a graph with vector embeddings. You simply add this additional parameter at the bottom here. That's the vector search configuration. And you specify the dimensionality of the vectors that you want to store. And then you can load the vectors into your graph through a fairly basic serialization. We'll also take a look at a Parquet example in just a second. So if we go back to the airport routes, and suppose that we have in S3 vectors, or we've made some LLM calls, and we've created vectors for our different airports, and we have those in a Parquet file, we can use the same kind of technique that we used before. In this case, we're using the Neptune.read function. We're calling it to read the Parquet file. But rather than federate the results or use them in a query, we're actually then matching on the airport codes and storing that embedding as a property in the graph. And then we can go on and do other kinds of vector search type operations. Now, another way that you can combine vectors and graph traversals is not necessarily starting with a vector search. This is an example that's a little bit abbreviated, but it's taken from one of the fraud teams at Amazon.com. And as you can imagine, on a site like Amazon.com, it's quite a challenge to keep up with various different kinds of bad actor type behaviors. One of the things that this group is looking at is who are trying to sell books that were generated by generative AI. And with the technique that they used was they started off by doing a graph traversal to match something that they had in their graph. So in this case, in their product graph. And in this example, I want to look at books about travel to Las Vegas. They took that graph search result, and then they combined it with the vector search. So show me books that are similar within some top K of the travel books that I specified in my graph. And then they combine this with information that they had in their graph already related to various different scoring that they use for sellers, listers, or buyers that have been flagged as suspicious. And so they can start with something they're interested in, expand out from the vector search to find other things that are similar to it, and then combine that with the relationships about who is known to be selling, listing, or otherwise producing this kind of content. So a very interesting way to combine the vector search with the structured graph piece. If you want to do more or learn more on this particular case, you can use this as also a Jupyter notebook that you can use to try and combine vector search with graph search. What else can you do with vectors and graphs? Well, one of the techniques that many people have used and tried is to use retrieval augmented generation to improve the accuracy of responses by bringing in specific data that might be relevant to your organization or to your business and using that to try and provide grounding. Well, with GraphRAG, you can take that sort of retrieval augmented generation architectural pattern and bring in some of the explicit information that you have from a graph. And we'll show you briefly an example where we're creating the graph automatically for you. But if you think about, in this diagram, some of the different kinds of algorithms that Umit talked about, there's lots of different ways that you can envision to combine these things. So you can do various different kinds of ranking or other pieces. So, there's a lot of different opportunity to use different combinations of techniques. With Amazon Bedrock knowledge bases, you can do this automatically. If you create a Bedrock knowledge base and you choose GraphRAG as the option, what will happen is in the generation of the chunks from your RAG application, we'll automatically build a graph. The graph is what we call a lexical graph. It conceptually looks something like this. So typically, a RAG application takes the documents and chunks the documents in some way, embeds, stores vectors along with those chunks. And in this case, when you use Bedrock Knowledge Base's GraphRAG, we also use an LLM to extract entities and facts that are occurring within those chunks. And so we automatically create a lexical graph behind the scenes. You don't need to have any graph expertise to be able to do that. But when you ask questions, and in particular, multi-hop, multi-stage questions where you need to assimilate information from multiple different sources to be able to achieve a result, you're able to get the benefit of the relationships and the connections in the graph in what's called the re-ranking phase. So typically, in a RAG application, you'll do a vector search. That vector search will have a top K and the top K results. There's often a re-ranking where you might take other kinds of metadata, or in this case, we're using the graph. And effectively, we're boosting the results that we're presenting back to the user based on explicit connections in the graph. And so as a quick example, if this document through this chunk was the top K result, or was one of the results turned in the vector search, these other documents may not have shown up. But because we have this lexical graph with these connections where we can see that there's a fact that's connected to these three entities, the re-ranking phase of this GraphRAG integration will effectively boost the results. And so that allows you to get more accurate results. So how well does it work? This is a case study from Trend Micro, obviously a computer security company. And they built a user-facing security chatbot. And they've built it and deployed it over time, combining various different techniques to build graphs, use GraphRAG, use Bedrock, use Neptune. And what they found over time, and you can see that this is looking at about 2 months of data. The full case study is available with the QR code. That over time, they were able to increase the accuracy of their chatbot from 70% to 90%, so higher is better here. And they were able to increase the user satisfaction. This thumbs down rate is getting lower over time. So they were able to produce more accurate answers, which also improve their user satisfaction. So that brings me to the last strategy. One of the things that obviously is very, very popular these days is looking at different ways to build agentic applications. And so if you look at a simple sort of agent dialogue, you might ask a question. Maybe I asked a question about something about my phone, and I gave it the model number. And then I come back a couple days later, and I ask another question that's related to my phone, and the agent asked me something that I think it should have known. So this sort of lack of context or loss of context means that agents aren't as personalized, and they're not able to respond as accurately to user interactions. And people often talk about this sort of the goldfish effect, where an agent without memory every interaction is like a brand new thing, experiencing it for the first time. So a way to solve this problem is to add memory to your agents. So this allows you to save and store the context of different interactions such that it can be reused at a future point in time. And there's lots of different potential applications for this beyond this sort of user experience model. You could, for example, think about if you had multi-agent workflows and they were doing plans. What plans generated what outcomes, and storing those kinds of things as memory. So there's lots of different potential here. There are different types of memory. So as a quick example, if you were to ask an agent to plan a trip to Tokyo with certain length and price parameters, and say, I'm interested in cultural sites and experiences, conceptually, you might break out the memories into these different types. And so you might have a working memory, which is things that were just asked in this current session. You might have had some kind of short-term memory concept where these are things that other conversations or other working memories that this individual or user has had. And then you might have something that was more of an organized long-term concept that you might know that they have traveled certain seating preferences, that they have global entry. And so if you're able to store and manage this context, you can use it within your agentic workflows and agentic interactions for both accuracy and latency improvements. There's lots of different ways to add agent memory. Fortunately, most folks are building inside of different kinds of frameworks. Obviously, the Bedrock Agent Core is one that we're using quite a lot. And so you can have different techniques to enable those in this framework. So you can use MCP servers to help you construct knowledge graphs based on memories or organization that agents have interacted with. Mem0 is an open source library that helps you do personalized knowledge graphs as part of your memory. Cogni is really more conversationally focused. And Zep Graffiti is really focused on temporal graphs. And there's lots of other different options. This is another opportunity for you if you want to go a little bit deeper here. This blog post was published last week. And it has code examples about how to use the Strands SDK, which is an agent framework that we have here at AWS, to be able to add and store persistent memory of different types. And again, that you can use that QR code. And so just to kind of give you a quick walkthrough of this example. So this is a Strands agent example. This is really, if you go to the blog post, you'll see there's really like 3 lines of code here to create this very simple agent. It's asking a question about the Mem0 project, and it gets a result. You can enable graph memory, which is, again, adding a couple of lines of code of Python code to the Strands agent. You can ask a question, what are the top contributors to the Mem0 project, receive the answer. And then when you ask another question, who works on the Mem0 project, you'll get both a faster result and a result where you have to retrieve fewer tokens. And so in addition to providing a benefit from an accuracy and user perspective, there's also a cost dimension. So again, how well does this work? These are some numbers that were presented by Zep and Graffiti. And you can see that using memories, they're able to get some improvements in accuracy. And very significantly, they were able to see almost 10x improvements in latency and the average number of context tokens used. So you're able to improve the latency and the user experience and also reduce the cost. So just to kind of do a quick wrap up, when you think about graphs as a tool to get more out of your data, and ways that you can use graphs to process your data where it is, and where you can use graphs in ways to improve the accuracy of different applications. Combine vector search and graph traversal to get the power of vector similarity search with the benefits and explicit information that you can get from a graph. And lastly, look at how you can store and organize agentic memories, particularly using graph structures with strands and Bedrock Agent Core. Thank you very much for spending your afternoon, or at least an hour of your afternoon with us. We greatly appreciate it. Umit and I will be around afterwards if anyone has other questions, wants to talk, and enjoy the rest of the conference. Thank you.